Hi, I'm Seth, and in this video, I'm going to talk about transformations. In particular, we're going to go over how to convert a distribution to z-scores and t-scores in Excel and R. But to start off, I just want to talk about what a transformation is. In this context, a transformation is a mathematical operation that you conduct on every value in a distribution. This will change some properties of the distribution while keeping other properties the same. So to start, I'm going to demonstrate some of this visually in Desmos. Don't worry about the formulas over on the left-hand side. You can just completely ignore all that for now. Let's say that we have this distribution of scores that you can see right here. The mean is 5 and the standard deviation is 2. This happens to be a normal distribution or a Gaussian distribution, but these transformations will work even if it's not normal. So the kinds of transformations we're going to talk about will move the position of the distribution along the x-axis, and it will also increase or decrease how spread out the scores are, but it's not actually going to change how the scores are positioned relative to each other. So for example, if score 1 was higher than score 2 in the original distribution, it will still be higher in the transformed distribution. The first transformation we're going to talk about is converting to z-scores. A distribution of z-scores has a mean of 0 and a standard deviation of 1, and we're going to see how that happens. Here's the formula for a z-score. Z is equal to each score minus the mean divided by the standard deviation. Desmos is trying to plot this, but I actually am just trying to show you a formula. So that means for each score in the distribution, we're going to subtract the mean, which is 5, and we're going to divide by the standard deviation, which is 2. Now, whenever we add or subtract a constant from each value in the distribution, that just bumps the distribution by that much along the number line. So right now, the balancing point, the mean is 5. If we added 1 to each score in the distribution, it would bump the whole distribution to the right over to 6. And that also just makes the new mean 6 because every score has increased by 1. If we now subtracted 2, it'd slide down to 4. Now it's hovering over 4. Okay, so we started out at 5. Now, if we subtract the mean from each score, that means we're subtracting 5 from each score. So here's what would happen. The distribution would slide over to the left along the number line until it was hovering around 0. This is the new balancing point of the distribution. Now, because the distribution is now centered on 0, if we multiply or divide every score by some constant, that's just going to change how spread out the scores are. So for example, if we double every value, the negative numbers are going to move off to the left away from 0, and the positive numbers are going to move off to the right away from 0, so it just becomes more spread out. There's actually twice as much spread now. You can see the standard deviation is now 4 rather than before it was 2. So originally our spread was 2. So if we now divide every score in this transformed distribution by 2, this is what we get. So we now have a standardized distribution where the mean is 0 and the standard deviation is 1. Because this happens to be a normal distribution, this is called a standard normal distribution, but you can convert to z-scores even if your distribution isn't normal. Now, converting to z-scores can be useful for comparing apples to oranges, comparing variables that were measured on different scales, or even the same variable that was measured on different scales. But let's do another transformation. Let's now convert to t-scores. T-scores are not the same as t-statistics, although sometimes if you're looking around online, you'll see people use these terms interchangeably. It's not a good idea. A distribution of t-scores is one where the mean is 50 and the standard deviation is 10. So now that we have z-scores, I want you to think for a moment. How could we convert this distribution so that its new mean would be 50 and its new standard deviation would be 10? what sort of transformation could we do similar to what we did to get here? One way we could approach this is using a modified version of this formula. We could say z is equal to a t-score minus 50 divided by 10. What we're doing is we're trading out t for x, and then we're plugging in the mean that we want and the standard deviation that we want. This formula basically says if the distribution had a mean of 50 and a standard deviation of 10, what score would a particular z-score correspond to? We can algebraically rearrange this to look like this: z times 10 plus 50. So what we're doing is we're multiplying each z-score times 10, and then we're adding 50 to each result. What this does is it's going to increase the spread from 1 to 10, and then it's going to shift the distribution so that it's no longer hovering over 0, it's hovering over 50. Okay, so I'm going to rescale this graph so that we can see this happen. So this is actually the same distribution, but I've zoomed out on the x-axis and I've zoomed in on the y-axis. When we multiply each score by 10, there becomes 10 times as much spread, as much variability in scores. And you can see the standard deviation has increased from 1 to 10. And then next, we add 50 to each score, which slides the distribution so that it no longer centers on 0, and it now centers on 50. And in this transformed distribution, the mean is 50, and the standard deviation is 10. So you can see -1 standard deviation is here. That's 40, which is 10 less than 50. And +1 standard deviation is here. That's 60, which is 10 more than 50. So what we've done is we've taken our original distribution and just moved it around so that the scores now hover around 50. And you can see that almost all scores lie somewhere between 20 and 80. T-scores are popular in clinical and counseling settings because they're in part because they're thought to be easier for people to interpret. So regardless of whatever your raw score on some test or scale or measure was, we converted it to a z-score, then we converted it to a t-score, and now it lies somewhere between 20 and 80 probably. The idea is that it's easier to interpret, maybe because there are no negative numbers and things like that. But hopefully what you can see is all we've done is we've sort of moved where the distribution is located on the number line, and then we've changed how scrunched or spread out it appears to be. But we haven't actually changed any particular score's location in the distribution. The highest score is still the highest score. The middle value is still dead middle in the distribution, and so on. But the kinds of transformations we're talking about, that this is all they do. So they change, for example, summary statistics like the mean and the standard deviation, but they don't change how the scores are related to each other. Okay, hopefully that made at least some sense, but now let's talk about how to actually perform these calculations, which turns out to be pretty easy. Okay, so first I'm going to show you how to do this in Excel, and then I'm going to show you how to do it in R. What we have here is a sample of 10 scores. I've already calculated the mean and the standard deviation. They're 9 and 5.16. So one way to calculate z-scores would be to manually plug in the formula. We could say this is equal to 9 minus the mean divided by the standard deviation. And I'm just referencing the cells. You could write in the values yourself if you wanted. That'd be pretty slow. But a faster way is to use this function right here. Equals standardize, then plug in a given value or set of values, the mean, and then the standard deviation, each separated by a comma. So we'll say this is equal to standardize, open parentheses, then just highlight the cells you're interested in, comma, mean, which is 9, comma, standard deviation, which is 5.16, and there you go. It calculates for all of those scores, the z-scores. And you can see the mean is 0 and the standard deviation is 1, as we knew it would be. Now to convert to t-scores, we can do something similar. Remember, we just multiply our z-scores times 10, then add 50. So this is equal to, highlight all the z-scores you're interested in, multiply them times 10 using the asterisk, then add 50. Boom, there you go. The new mean and standard deviation are 50 and 10, as we knew they would be. As promised, the smallest number remains the smallest, no matter whether it's in raw form or a z-score or a t-score. It remains the lowest value because these transformations aren't changing anything like that. And the highest value is the highest no matter whether it's a raw score, a z-score, or a t-score. So that's pretty easy to do. Now let's jump over to R, and I'm working in RStudio as I always do. Here I have the same distribution of scores. This code allows me to save these values as what's called a vector in R. And you could kind of think of that as a single column of data or a single row of data. So I run that. Now, if I were to run the code X, just X, I get these values, 9, 9, 2, 5, 9, 7, 18, 10. The same values that we had from before. I can find the mean and standard deviation using this code. Mean of X is 9. Remember, that's what we got with Excel as well. And SD, open parentheses, X, that gives us the standard deviation, which is 5.16. Same answer we got before. To convert to z-scores, one way you could do it, let's say I'm gonna give it let's say xz. So that means our original scores, our x values, transformed into z-scores. That is equal to, and then we can just use the formula for a z-score. We could say x minus the mean of x, divided by the standard deviation of x. Okay, and we'll run that code and then see what we get. Yep, here we go. These are all the exact same z-scores that we found in Excel. The first two are 0 because those scores are 9 and we're subtracting 9 from them. So that they're right on the mean. There's our lowest score. A 2 is converted to a negative 1.36 when it's a z-score. We can find the mean of these z-scores, which we know it's going to be 0. It is. We can find the standard deviation, which we know is going to be 1, and it is. You can see the console is it's printing the results. We get 0 and 1. Now to convert to t-scores, let's say xt, and that will mean x converted to t-scores. And we will take xz times 10 plus 50. And then I'm also going to tell it to go ahead and tell us what the result is. There we go. 50, 50, 36, etc. And let's find out what the mean is. We already know it's going to be 50, and we already know the standard deviation is going to be 10. So that is how you can convert to z-scores and t-scores in R. Okay, hopefully that was helpful. Hopefully it gave you a little bit more intuition about how these transformations work and what they're actually doing to the distributions. And now you should be pretty comfortable conducting these calculations yourself in Excel or R. Okay, that's all for today. Let me know if you have any questions. See you later.